All right, I know this is like a little intimate setting here, and I'm going to use the mic just because we're going to record it. Very professional here. Thanks for coming out. For those of you that aren't BloomReachers, very happy to have you here. I've actually had the pleasure of listening to this talk that Corey gave. And well, first, I guess, Corwin is an engineer at BloomReach. I'm also an engineer. I'm Stormy at BloomReach. And like BloomReach's headquarters is in Mountain View, and I was lucky enough to listen and participate in Corey's talk in Mountain View. And phenomenal talk. It's one of those that, like, there's a lot of tech talks that don't go kind of deep enough, and they're just very high level. But Corey is certainly a subject matter expert in containers, developer operations. So there's tons of stuff to learn from him, and particularly this talk. And it seems like the industry is certainly moving this direction. So the more you can learn about this stuff, the better. And I guess, Corwin, are you ready to go?
Absolutely, I am. So, hi, everybody. Woo! Yeah, thank you. We gotta build it up. Come on. Gotta have some energy, right? So, hi, everybody. Everybody who I don't normally see, thank you so much for coming. I especially appreciate it, given all the circumstances. So again, my name is Corwin. I'm going to talk a little bit about containers. So let's get going. Okay, so a good place to start seems to be with who am I? My name is Corwin Brown, but we're all friends here, so you can call me Corey. Traditionally, I come from a DevOps background. I've worked at places like the public cloud at Rackspace. I worked at Fitbit, and I've worked at many more companies nobody's heard of and don't really matter. I'm currently a full-stack software engineer here at BloomReach. Also, I'm 30 years young, a Gemini, and to answer everybody's first question, about 6'8". So what is it that we are going to talk about today? Well, we're going to talk about containers, obviously, because that's what the title said. But first, I'm going to talk a little bit about the definition of DevOps, because I think that is an important foundational piece that we should all kind of care about, because it really answers the question, especially if you come from a software development background of like, why does any of this matter? Why do I care? We're also going to go into a Linux crash course simply because the rest of it won't make any sense if you don't have some foundational Linux knowledge. So we're going to go into a little bit of that. We'll talk about what containerization even is. We'll talk about the history of containers because they are actually much older than you might think. And we're going to talk a little bit about how containers work, namely process namespaces and control groups. And we'll also talk a little bit about how we use containers here at BloomReach and just how you can use them to be successful if you're kind of like, hey, they seem cool, but I don't know what to do with them, which is, I think, where most people are most of the time. So to start us off, I'm going to get up on my soapbox and talk a little bit about the definition of DevOps. And DevOps is kind of one of those things that, depending upon who you ask, you will almost always get a very, very, very different answer. So I thought it was important to get a definition out of the way so that way we could all have the same foundation. And the definition that's always really worked for me is that DevOps is about recognizing that backing infrastructure is a vital part of your application and not separate from it. You shouldn't treat them as two separate problems. You should at least make some attempt to understand everything from like the very tip of the front end all the way down to the base level if you can. You should have some idea of what's going on there. And so let's get started with a Linux crash course. So an important concept in Linux that kind of comes into play with some of the earlier containerization technologies is that every single thing in Linux is a file. Everything is represented as a file. Block devices are files. Network sockets are files. Named pipes are files. Terminals are files. Directories are files. Files are files. Files are basically the primary Linux primitive. Everything is built off of that. For example, your hard drive is at dev SDA1 or whatever. Your terminal is at dev at TTY. Alternatively, you have the entire proc file system, which has actual file system APIs that tie into the kernel, and that is how you communicate with it. So everything in Linux is a file. And that'll come up later, spoiler alert. So you also need to understand that the difference between user space and kernel space. So user space is the section of system memory that all user processes run in. So that's like where y'all do stuff. And then that is contrasted with kernel space, which intuitively is where the kernel runs system processes. And as a user, you do not have access to kernel space. And that's kind of an important distinction to understand, that like there are parts of the system that you don't get access to. Yeah, and so you would communicate with the kernel by using things like syscalls, which whenever you have a hypervisor, that is often just a wrapper around syscalls and provides like the ability to filter it and that kind of stuff. And that can be important later. There's also the concept of fork and exec. So processes in Linux are created using a fork and exec paradigm. So what that actually means is that a fork gets called, which copies an existing process into a new slice of memory and then returns the newly created process ID. So fork is said to be called once and returned twice. So the parent gets a return and the child gets a return. So the way this kind of works is, let's say you have a shell. Like you just bin bash whatever, and you type in curl google.com, something like that. What actually happens when you hit enter is that shell will fork itself and copy all of its memory into another section of memory and copy itself entirely. That new child process will get back a PID of 0, which is how it knows it's the child process, and then that child will then call exec, which replaces the current running process with an entirely new program. And that's how shells work, and that's the basic process model that Linux follows. So now that we've kind of gotten all that foundational junk out of the way, let's talk a little bit about containers. So what is containerization? Simply put, they're an operating system feature that allows for the existence of multiple isolated user spaces. These isolated user spaces are known as containers. Each container is only made aware of a specific subset of its host machine's resources, and a container is capable of containing anything from a single running process to an entire operating system. Now, a caveat here that's kind of important, and this is why I brought up the whole user space and kernel space thing, is that containers are entirely a user land concept. Like, there's no like system equivalent. The system doesn't know you're doing that. The kernel is completely unaware. In fact, what you're actually doing is sharing a kernel between multiple different user spaces. So it's kind of important to know that like you're faking it. The kernel doesn't actually know you're doing something different. Yes?
Are we allowed, one thing I wanted to check this mic, but are we allowed to jump in with questions?
Please do.
Okay. I was going to ask, how is a container different from a virtual machine?
Well, that's a very good question, and happens to be relevant to this very slide here. So containers, as you might be saying at this point, sounds an awful lot like a virtual machine, and that is reasonably accurate. So they are very similar to virtual machines, but one of the big benefits of them is that you don't have to maintain another operating system install. And like, it's really easy to hear that and just be like, well, I didn't have to go through the Ubuntu setup steps. And like, that's true. But it also means that you don't have to manage like a whole bunch of different backup policies for machines. And that can also be like the actual physical data and the cron job that schedules it. But it's also like the backup policy of like, per some regulation, I have to maintain a copy of this for X number of days or something. And it's not necessarily that you don't have to worry about backups anymore. It's just that it's entirely separate from your application. If your data is separate from your container, you can treat them completely differently. It doesn't matter anymore to the application. You also don't have to worry so much about doing like massive upgrades and patches. So an example of that would be, let's say tomorrow OpenSSL has some new like really, really bad bug, as it seems to have every so often. No longer is it like, oh, well, I got to take down my infrastructure and do this thing. Like, no, we'll just rebuild the container and redeploy it. I no longer care about that machine anymore. And you can run any popular Linux distribution you want. So like, let's say you're in a situation where like the sysadmin at your company really, really loves Red Hat, but you're a Debian guy through and through because it's more stable, or whatever your reasons are. It doesn't matter anymore. Run on whatever version of Linux makes sense to you. If you want to use apt-get instead of yum or apk more flow-turbo, whatever, it doesn't matter. They also tend to be lighter weight in VMs, and like each virtual machine requires significant overhead that comes alongside with running an operating system. I've already mentioned the human time, but there's also the compute time that has to go with that. So if you're emulating an operating system, every bit of CPU utilization that goes towards that doesn't get to go towards your application. So this can lead you to a situation where, like, if you have a virtual machine that is running, like, let's say your application tops out at like 70% CPU utilization, but is idle from time to time. Every time that it is idle, and every bit of that every time you're not maxed out at 100% CPU and memory, you're wasting money on that machine. Like, it is by definition over-provisioned. So the whole idea is that since containers are lighter weight, you can run more of them on a single machine, which means you can bin pack as many as you want, and you can actually get what you're paying for out of that machine. So let's talk a little bit about the history of containers, now that we've gone over a little bit about what it is I'm even talking about. So containers actually kind of started with something called a cheroot, which is kind of like the proto-container. It is a portmanteau of change and root, and it provides file system isolation. And it provides file isolation by changing a user or a process's logical root directory. So what this could mean is Jenkins is actually a pretty good example of when it would be appropriate to use a cheroot. So if you've ever used Jenkins, by default, its home directory is at varlib Jenkins. What if you could tell Jenkins that, like, nothing else exists? Your root directory is varlib Jenkins. If you have a machine that developers have access to, you're in kind of a safer position now because they don't have a way to, like, back out of that and do something shady. For example, a Jenkins machine has been broken before at one of my previous jobs, and I was able to just echo my SSH key into authorized keys, and I can now access that box and do whatever it is that I want to do. So if I do a cheroot on the Jenkins process there, I'm not capable of doing that because as far as Jenkins is concerned, no other directories exist. So there was a system call that was introduced in version 7 of Unix, which is 1979, called cheroot2. If you're the kind of guy who likes to go read man pages, that will be what will get you there. And since everything is in a file in Linux, as I mentioned before, this actually will get you pretty far as locking in a user to do something. After that, we kind of got FreeBSD and Solaris, or FreeBSD jails and Solaris zones. So as you can see, these were released in 2000 and 2004 respectively, which meant that we went, like, 20 years without any new container improvements. But these provide file system and network isolation. Zones heavily utilize features in ZFS, which if you're not familiar with, is a Solaris file system that is generally pretty good for NASs and does a lot of, like, interesting things. It's definitely worth reading up on. But I'm a Linux guy, so I don't really know a whole lot about these, and I don't think they're super interesting. They're not really widespread use. They never really caught on, but they do have an important spot in history. They're actually very, very similar to LXC containers, so I'm actually going to talk more about those. So LXC containers stands for Linux containers, and they are very, very, very similar to FreeBSD jails. And they're generally meant to be used more similarly to a virtual machine as opposed to, like, what you traditionally think of as a container. So you would actually run your entire operating system. So it would have its own, like, init system and all that good stuff. And as a side effect of that, LXC containers tend to be less portable than the containers people tend to think of. And this isn't a flaw in LXC, it's just that it's a very raw tool. Like, it doesn't wrap a whole lot for you. It doesn't give you a lot of niceties. And because it doesn't do that, like, yeah, sometimes if you have, like, some driver mismatch, that's still gonna ruin your day. But they are really designed to be a self-contained user environment as opposed to a self-contained process environment. And they also used to be the backend of Docker, which is a fun little bit of trivia. But LXC is generally the right tool if you're wanting to do, like, things that need to be very performant, but also need to be isolated from other things on the system. So if you're thinking, man, this should really go in a virtual machine, it has to do all of these things, it really needs its own init system, these signals matter, and I don't want to lose them, but for whatever reason, I need bare metal performance, LXC is actually a pretty good choice. In fact, when I was at Fitbit, we used LXC containers quite extensively to do, like, management operations. Like, for example, our Puppet Master was an LXC machine. After that comes Docker, which has kind of become the Kleenex of containers. If I say Docker, and kind of synonymous with containers at the moment. It is very much the fan favorite, and I think it's kind of won where it is, it's stationed where it is today by having a good, like, user experience and environment. Like, the whole idea of shared containers is a first-class concept in Docker. It also provides a lot of management niceties, like Docker networks, if you haven't used it. freaking amazing. They're awesome. They work really, really well. It also handles file system mounts really well. You have composition options with things like Docker Compose. Orchestration, there is more than I can name and released every day, such as Docker Swarm, Kubernetes, Mesos plus Marathon, all of that. Plus, Docker files, honestly, is kind of a killer feature for me. The ability to be able to define specifically what I want my container to look like in the end and then have that just go happen, I think is incredibly important and very, 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 very valuable. The last one to talk about, I think, is Rocket, because I think it has some potential to be the future. This is actually being developed by a company called CoreOS. It is free and open source, all that good stuff. And it has a lot of second-comer advantages. So all of the things that Docker is today and wasn't yesterday, Rocket is today and has always been, which I think gives us some advantages. It also follows a more Linux-like process model. So Docker, interestingly enough, is actually a client-server model. So there's a Docker daemon server running in the background, and the Docker command line client you interact with is actually like a client to that it communicates over a network socket, which you might notice if you ever run into oh, Joey has a question. He's holding the microphone. Oh. Joey's asking about a Docker file. Oh.
Holy moly. It suddenly decided to work.
He's much more louder.
Yeah, these microphones are a little testy. That Docker file, is that something that wasn't available in the Linux container in the raw state, that LXC? And that's is that why Docker became popular? Or is that, what would you say contributed to its success in capturing the Kleenex title?
Well, Joey, as you would see on this slide, I think it is primarily because of shared images. But no, seriously, joking aside, I do think Docker files played a big part in it, and no, LXC definitely did not have those. You would provision it like you would a virtual machine.
So that's like a distinction there.
It absolutely is.
Does Rocket still have that same Docker file syntax?
Yes, it absolutely does. So it has its own similar kind of thing. In fact, Rocket is generally backwards compatible with all Docker features, which we have here because it's built to adhere strongly to the Open Container Standard, which would be a slide against Docker, but it is based on the Docker image. So everything Docker can do, Rocket can do.
What sort of properties might I give a Docker file? Is that defining, that's certainly not talking about defining some processor speed like I'd be used to in a virtual machine. What sort of definitions am I giving there?
So with a Docker file, you would do things like, I want to be sure this image contains these packages. So for example, let's say you needed an Nginx web server for some static content, right? So you've got some HTML files on your machine and you want to serve them via Nginx. Let's say that's the end goal. You could, if you were familiar with Ubuntu, start with an Ubuntu base image that is provided by Canonical. So your first line of your Docker file would be from canonical/Ubuntu 1604 or whatever. And then you could install Nginx onto that machine. So it would be apt-get install Nginx, just like you're used to. And then you can actually add your static files to that directory or to that container or mount them, depending on what you want to do. And then do a Docker build. And then at the end of that process, you will get a Docker container that contains a running configured version of Nginx and all of your static files. Then once that container is complete, you can pick it up and move it wherever it makes sense for it to live. So from your laptop to production. That's kind of really the container goal, right? Is that whatever you have on your laptop should reasonably mirror production. Does that answer the question at all?
Cool, yeah. No, that's helpful.
Right on. Cool. So as I was talking about with the process model, Docker follows a client-server process model, which is certainly fine. In fact, what that really means is that every time you launch a container, it has a supervisor or watchdog process. So you can say things like, ensure this container is always running. It cannot go down. So that way, if that container dies, Docker can go ahead and restart it. The downside of that is a lot of Linux purists will argue that, like, well, I have one of those, and it's called an init system, and I've had one forever. Why do I need Docker to do that for me? And that's certainly a reasonable argument. And Rocket kind of follows that model of it just forks out a new process that contains that container, and then init or systemd or upstart or whatever now owns that process, and you can use your native process manager to manage that. I think that was more of a problem before the whole community decided it was okay with systemd. So apparently having a process that does a million things is fine now. But as I was saying, Rocket is built to adhere to the open container standard, which would be a slide against Docker, but it is based on the Docker standard. And as such, it can be a drop-in replacement for Docker. So I could really see Rocket being potentially the future, depending on what Docker decides to do. So, or the metaphor I have here is that it might become Linux to the Docker's Unix, depending on the direction of Docker's focus in the future. And the reason I say that is I could see Docker very much going like the Red Hat model of like, use my free product and then buy support from me. And you kind of see that in like their adaptation of Docker Swarm and like trying to really kind of bite off more than they can chew and trying to be a bigger product than as opposed to the Unix process model of like do one thing and do it well. But they've also kind of backed up on that now and are going all in on Kubernetes, so who knows what they're going to do. But I do think Rocket could be a potential candidate for replacement in the future. So moving on from that, let's talk about how they actually work. And this is the neat part, I think, or the part where people's eyes will glaze over, depending on your interest. So there are two primary kernel features that allow containers to be a thing. Those are process namespaces and control groups. So to process namespaces were added to Linux in 2002. They started with the mount namespace, and we'll go over what all of those mean in the next slide. But more have been popping up since about 2006. And this allows the kernel to isolate system resources. This is kind of like a chroot and actually operates similarly, but for other types of resources. And as opposed to being ultimately a mask, which is what chroot is designed to be, this is like those other things don't exist. You are only presented with a subset of resources. There are 7 kinds of namespaces, and a process can be assigned to a namespace in any one of them, many of them, all of them, take your pick. And the namespaces that exist are as follows. There's mount, which limits what mount points are visible to you. This is similar to a chroot, but not the same thing. So a chroot is saying you only are, this subset of this file system is visible to you. Mount is saying you only know this mount point exists, which sounds like it's just a pedantic difference, but it is important because one is what you can see, one is these other things don't exist. There's also a PID namespace, which limits the awareness of other processes. So if you're in this, you might not, you only know a certain subset of other processes exist. There's the net namespace, which does a little bit more in that it actually virtualizes the entire network stack. So this is what allows Docker containers to have different IP addresses from your host machine. There's also an IPC namespace, which limits inter-process communication, primarily via walling off shared memory. There's UTS namespace, which stands for Unix time sharing. And that's a super duper weird name, but all it really means is that your container is allowed to present a different host name than the host. So your Docker container can be called like my thing number 1 as opposed when the host name command is run, as opposed to like my thing number 1.mybusiness.com or whatever. There's a user namespace, which limits what users are available to, or visible to a process. And then there's the C group namespace, which is kind of a weird meta one. What this actually does is it prevents a container from knowing, or rather it prevents whatever is running inside of that namespace from knowing it is in a C group. So this is kind of like, you don't need to worry about it. This is just the environment you're running in. You cannot discover that you're actually being limited. So let's talk a little bit about how that actually works in like a more practical example. So if we had a shell available, we could actually run this command on any Linux machine. So unshare means like I'm unsharing from shared system resources. I'm going to my own corner. We're passing in the -- fork command, which is exactly what it sounds like if you recall my fork definition before, that it forks out a new process. -- net says give me a new network namespace. And this is the process I want to run in that namespace. So in this case, it's just bin bash. So if I had like a normal shell on an Ubuntu 16.04 VM, and this is just like, I literally just did vagrant up and then typed IP link is what this is. And as you can see here, what we get back is like our standard loopback address, as well as like the address that points to our actual network interface. But if I do it in my namespace shell that I created before, I'll actually only get the loopback address back, because that is all it knows exists. I haven't presented it with any other network interfaces. So yeah, it has no knowledge of what's going on in the system. And this is interesting, but let's actually like go into, there we go. Now we have actually some C code that demonstrates what's going on here. So I'm going to walk over this line by line, and you'll note that this is really bad C code because it doesn't have enough if statements in it. So if we start here, we can see we have our int main. We have like, I'm printing a little header just for the sake of like having a nice little header and showing what's going on. Then we're calling system IP link. So system just opens up a shell and executes whatever this string is. So that's all that's happening. We have a little divider here. Then we have int clone flags, which I'll go into in detail on the next slide. Then we have child PID here, and it's calling out to the clone syscall, which again, I'll go into more detail here in a second. So what I'm passing clone syscall is this child exec function. So that is up here. All we're going to do is say we're in a new namespace, and then again run IP link. And the parent process here will wait for this child PID to complete, and then we'll exit success. And this will actually produce the exact same output as what I had before in the previous two slides. So to go into a little bit more detail, if you've done any systems programming, this will look very familiar to you. The way you generally construct options in like low-level stuff is you'll have like this enum that is actually some numerical value, and you'll bitwise OR it with the other flag you want to do to construct your argument. So when we say, I'm preparing my flags here, the first flag is sigchild, which just says when this process exits, the signal you'll send to me is sigchild, which is a standard behavior. But we're ORing it with clone new net, which says, hey, give me a new namespace, give me a new network namespace. So as we call clone here, this first parameter is the actual code we want to run inside of this new process. I have to provide it a call stack, which is a difference between clone and fork. But this call stack is just a pointer to some array in memory. It doesn't actually matter what it is, doesn't need to be, we don't have to worry about it too much. Then I pass it that clone flags, and this null would actually be an argument vector if I was to pass arguments in, but I'm not, because this program is real simple and dumb, and because anything more complicated wouldn't fit on a slide. So yeah, the big point about creating process namespaces, and the things I wanted to point out, is that it uses clone instead of fork. So as I said before, generally the process model for 30, 40 years has been to call the fork syscall and then to call out to the exec syscall. So this instead uses clone. And clone is really just an updated version of fork. It has some new features, primarily of which, and the most interesting for this, the sake of this, is that it allows for the creation of new namespaces. But it's kind of an interesting side note. In newer versions of the Linux kernel, fork is just clone. Like it literally just calls out to clone under the covers, which I think is neat. But it is important to note that this is a Linux-specific syscall and is not POSIX compliant. So if you've ever wondered, like, why do I have to run this weird Docker for Mac native thing? This is why, because OS X is based on FreeBSD and not Linux. So it actually does not have this syscall, which means it has no concept of namespaces. So now that we've talked a little bit about that, that actually brings us to control groups, which is the other side of this coin. This became part of the Linux kernel in 2007. Development began on it at Google in 2006. And Google, you may or may not be surprised to know, has been using containers like forever, basically since their start. Whether it was the Chroot variant or their own custom thing that now became control groups. So control groups are a feature that accounts for, or limits accounts for, and isolates system resources. So if namespaces control like what is visible to you, control groups control what you can actually do with those resources once you have them. So they provide resource limiting. So this is like process A only gets 1 GB of memory, super simple. There's also prioritization, so you can say like, well, process B gets 25% of my CPU, while process C gets at least 50%. It provides accounting, so you have the ability to say like, well, process A is using 125% of resource X, and they should be billed accordingly. And when I say billed, I mean like maybe your organization has like a performance budget that you have to meet, like you can only use so much of the resources, or maybe you're renting time and they're actually literally billing you. That's what that service is provided for. It also has a control functionality, and this one's a little bit harder to explain, but it allows you to like freeze the in-memory state of processes. It allows you to like do snapshotting or like restart groups of processes. It's like a way to manage multiple things all at once as they might exist in that control group. So let's take a look a little bit how this works. So like most things with Linux, C groups are actually represented on the file system. So that was what that slide was at the beginning all about. So if you were running an Ubuntu 16.04 system, you'll actually find them at sysfs group or fsc group. Inside of that directory will be all of the C groups available to you, and it'll look like this. So this is literally just a Xennial virtual machine. I did vagrant up and then all of these commands. So if you list inside of here, you can see all of these guys. These are all of the resource types that can have a C group. So for example, you could have a C group that limits what you can do with block IO devices, what you can do with the CPU, what you can do with memory, what you can do with various process IDs, that sort of thing. And if you do like drill into one of these, so like for example, I've done an ls-l in memory, you'll see all of these files here. And these aren't files as you traditionally would think of them. These are actually an API to speak with the kernel. So if I were to cat out, I don't know, limit in bytes or something, I would actually get just an empty file that contained only a number. And that number would be whatever the global memory limit is in bytes. So let's say I want to create a new C group. So I can do it with this cg create command where I just say like, well, I want to create a memory control group and I want to call it test group. Alternatively, and I think this is super neat, I can also just mkdir in like a directory there and that will work. That will be, these are effectively the exact same. And after I do that, we'll see here like, oh, I have a new C group right here. So this is ls-l, that memory. So we're at sysfs C group memory. You'll see all of these knobs that we can turn. And then we now have this group here. So and if I do an ls-l in that group, you'll see that we again have all of the same knobs. We also have this tasks file here, which if I want to add a process to a group, I can either use the cg classify command where I pass in the group I want to pass it to, so memory, test group, and this is the process ID I want to live inside of that C group. Or alternatively, I can just echo the string of that PID directly into that file and it will just work. So for example, if I wanted to like change this limit in bytes, all it is echoing the string of some number into that file and it will immediately take into effect and that process will immediately be constrained. So that's kind of neat. So in summary for all of this, like control groups control how big your slice of pizza is. Namespaces prevent you from ever knowing there was more pizza. And if any of that is interesting, some other reading that that really kind of helped me come to terms and understand how these things work is there's a Docker clone implemented in Python called Mocker. It was a project that a gentleman wrote, and he claims 48 hours. It doesn't have some of the niceties, but it will set up complete container isolation for you. This gentleman called Nigel Brown, I guess he's named Nigel Brown. That's probably his name. People don't just call him that. But he has a deeper dive into namespaces at his blog here, and then this Crosby Michael gentleman also had another blog that I found very helpful, but it's incomplete. So he has a Creating Containers Part 1, and there is no Part 2, but Part 1 was very helpful. So we've talked a little bit about what containers are, how they work, and the history of them. Let's talk a little bit about like, what does this do for me? Like, why do I care about this? So one that kind of came up for me is we had to write a tool that did monitoring and alerting, right? So at BloomReach, we get in data from customers. We wanted to know like, well, if we don't have data for a while, I need to send them a notification, right? They probably want to know about that. And my thought process was like, well, monitoring tools exist. Do I want to write one? And so I needed to kind of test out some technologies. And when I was at Fitbit, we had used a tool called Prometheus that I really liked and I thought had a good general model of how to do things. So I was like, okay, well, like, is there a Docker container? Can I just install this and play around with it? Like, do I have to spin up a VM and go through the whole shebang and whole process? And it turns out that the first hit is on Docker Hub, and it's a Prometheus. So it's like an actual official Prometheus image. And I pulled it open, and sure enough, it is supported by Prometheus. It is their official recommended way of doing things. So I pulled open my shell, and inside of that documentation, it told me I needed to expose port 9090. So I just did a docker run --rm. --rm means like once the container exits, don't like keep it around, just clean it up and close it. I did a -p 9090 to 9090, so that exposes the container port to my host port, and I want to run the Prometheus image. And then it starts doing a whole bunch of stuff, and some text starts scrolling across my screen, and all of a sudden, boom, I can actually get to a testable Prometheus cluster. So this is incredibly valuable because within like 3 or 4 minutes of actual work, I can now test this to see if this will be a good harness for my application. I didn't have to install anything, I didn't have to manage anything. It was all easy peasy lemon squeezy. So there's also like dependency requirements. So like let's say you're developing an application and it requires Postgres 9.6. I don't know why 9.6. Let's just say 9.6 has some special feature that you absolutely need, and anything newer it breaks, anything older it just doesn't exist. So if you pull up, like, for example, the official supported Postgres image, you can see that, like, oh, well, they have all the different versions of it. Well, that's super neat. So then I can, again, run a similar command of just docker rm, or run --rm Postgres 9.6.6, and I immediately have a Postgres database that I can start developing against immediately. And that's incredibly powerful and compelling. Another argument for it would be like developer onboarding. So we recently hired someone, actually sits at this desk right here, and we needed to get him up and going. And previously, getting a developer's like environment set up like is a non-trivial task. Like it ended up taking like a week or two of just like, oh yeah, no, you got to install this weird thing, but you need this version of protobuf, or like it's got to be this strange thing, and all that good stuff. So now it's just make setup. Like we just have a make file that goes and downloads all of the Docker containers they need. So in this case, like this will set up a Postgres database that already has production-like data in it. It will spin up a version of our application inside of a container. It will set up a network so that way they can communicate with each other. And I didn't have to do anything. So now it went from a week to get a new developer set up on a project to like 30 seconds. It's been amazing. There's also like end-to-end testing. So very similarly, we now just have a make test command and what this actually does for one of our newer products is it spins up a database with production-like data and several instances of the application and allows it to test against an actual database. So this is important because now we don't have to deal with mocking. Anybody who's talked to me about testing, which not many people, admittedly, knows that I'm not a big fan of mocking because at a certain point with mocking, you're ultimately testing like, does the return keyword work? Spoiler alert, yes it does. So this allows us to actually test against actual data in something that resembles production as opposed to assuming our mocks are maybe good enough. But also talk about building, because like I know a lot of times as developers, you might not have like root access to your developer or to your build machine. So what happens when like, well, I'm doing something new and cool, I'm using like the newest version of Webpack and I need like Node 8, but the build machine has Node 5, like what do you do in that situation? Like, well, Docker makes that super easy. Like, and this is actually one I pulled for one of my projects here, because I ran into this exact problem. So I just pulled down Node 8, pulled in my application, and built it. And then this built it and spits out the actual artifact to a mounted directory that I have access to. So I've effectively built my application in a like closely guarded, hermetically sealed environment, which I think is very valuable. And like this kind of leads to where I think the future of all of our jobs is going. We need to get out of the business of caring about servers. Servers don't matter. We need to think of them as cattle, not pets. We don't need to be naming them anymore. And we need no more special purpose machines. And this can be anything from like, if you're writing directly to disk, you probably shouldn't be doing that unless you really need to. Like, let's write to a database. Let's write to an NFS share. Let's write to anything. Let's make that machine no longer special. And if you can do that, that leads to the idea of a data center as an operating system, which is what like the Marathon company is kind of based on, or Mesosphere. That's what they're called. That's what Mesosphere's kind of like mantra is, right? Is the whole idea is that Mesos or Kubernetes or whatever is really a kernel, right? It's just a kernel that instead of talking to various CPU cores or bits of memory is talking to a data center worth of cores. So instead of a single core, it's now a computer. That computer is now a single compute unit that can be utilized and split up. It's really just another place for, or rather another way to think of that would be a data center is really now just a bag of CPUs. Like let's just schedule it on one of the CPUs. I'm not particularly interested in which one it is. And this really kind of goes back to ensure that you're getting the utilization you pay for. Like if you can schedule these things efficiently and they're reasonably lightweight with very little overhead, then you can actually get what you pay for. Like you can get the most bang for your buck. And yeah, that's what I have. Woo! So thank you guys for coming. I appreciate it. I hope you enjoyed any of that. And have a beer. Do what?
Do you have a question, perhaps?
Oh, I do have a questions phase. Sorry, I forgot about that.
Let me come over here.
Oh, I forgot to do questions because I'm a bad speaker.
So Corey.
Hi.
First off, that was a great presentation.
Thank you.
Just want to let you know, I actually went to a one-day workshop last year at Google, like Google Cloud's next thing, where we just went over containers.
Mm-hmm.
And I can say your information was a lot more clear than you were there.
Yes.
You did an amazing job. I really have
Give me a high five.
And so I just want to tell you thanks for that, because you did a great job.
Well, thank you.
So I have 2 questions for you.
Hit me with it.
And let's see, one of them is, we put you know about containers and how you use them. Are there any times that you think a VM is better than a container or provides better efficiencies?
Better efficiencies, I think, is arguable. Most of them would be security related because you can filter out syscalls, and if you run in a Docker container, by default, you are root. And that means depending on what file mount you've provided, you can get into some nonsense with that. There are ways around it, but they've all been super hacky. So like Fitbit, it's fine. So at Fitbit, the way we handled this was we actually just ran our Puppet code on a Docker container that would create every user that we expected to exist. And so then you would still run as your user, which I thought was a fine answer. I also recently had the pleasure of speaking with Facebook about some of their stuff, and they actually do something very, very, very similar. So apparently that's a way some people are handling it. But the ultimate time where I would choose a virtual machine over a container, despite some of my examples, is if I had to run a production level database. I would generally not run that on a container, primarily because it requires, like by definition, a very secure disk. That disk also shouldn't disappear at any point in time. And because Docker uses, oh, this is a specific Docker problem, because of the file system it uses, you actually take a hit on I/O. So if you had a very, very I/O dependent application, virtual machine is probably the way to go.
One more question.
Do it.
All right, so you mentioned that Docker uses a client-server model.
Mm-hmm.
And I was wondering, because I don't really understand how they work together, do you have to use the IPC process group, or is that used as part of that client-server model? Or, okay.
Nope. There is, by default, it is var run docker.sock. It's just a named pipe file.
Gotcha.
Yep.
Okay.
You've probably tried to run Docker, and it's been, you need to be root, and that's why. In fact, you can actually do something really cool with that we're doing now is I have a Jenkins instance running inside of a Docker container, and it needed to be able to spin up children Docker containers. So what I actually did was mounted the parents docker.sock, which gives it the ability to not create children containers, but sister and sibling containers, which is super, super neat that just works that way. Anybody else have any questions? Oh, Scott's got one. That's not fair.
Earlier you had mentioned that you can kind of echo out numbers in some of those C group files to limit like a C group's memory usage or something.
Mm-hmm.
This is probably a little bit inside baseball, but does that limit individual processes in that C group to that limited amount, or does it limit the overall C group to that total amount? Meaning there's 2 processes, would they each individually be restricted to a 50 megabyte limit, or they each be limited in the whole to 50 megabytes?
So my answer will be an assumption and an educated guess. My educated guess is that it is for that C group. So that C group is restricted to that because that would make sense in the context of containers and how they generally, that matches with my personal experience. Oh. Well, good, because I'm lying.
Based on your experience, when would you choose a container over maybe starting to choose more serverless style architecture?
So I actually think the two are generally fairly comparable. So what I think the future will be for that kind of question is it is not uncommon today for a company or a SaaS provider to be like, hey, here's a webhook. Right? So like whenever we do something on our end, we'll fire a GET request to this. Well, in order for that GET request to work, you have to have something for it to hit, right? Like maybe you're running on Heroku or something and it's easy, or maybe you have like a very experienced admin team and they have like an AWS setup. But maybe you're just like someone's Etsy shop, right? And they don't know anything about that. I could potentially see a future where there's like a GUI where you ultimately configure a Docker file that fires it off to someone's cloud provider, and then they just run that Docker container. So I can kind of see that coming in, but in general, where I kind of see things like serverless coming into play is largely for complexity. So if you need to just like, I'm serving an API that hits a database and does nothing else, like, yeah, that makes sense for serverless. And you could absolutely run that in a Docker container, but it's more of like, what maintenance burden do you want? You know, if you're willing to put it onto if you have a Mesos cluster and you're a big enough company to already have that, then yeah, just run it out there. It's fine, no big deal. You probably already have the orchestration to do that. But like something that we run into is we don't have a Mesos cluster. So like if we don't already have that in there, then yeah, I can get a Lambda job running in 10 minutes. That might be the better solution. So it's really more about what resources you already have available. All right, anybody else? Oh yes, this guy, hand him a microphone.
Googling things like, is Docker good? Is Docker bad? And I came across a blog post that was called Sad State of Sysadmin in the Age of Containers.
Mm-hmm.
People were, I think, upset that there's like downloading unassigned binaries. Right?
Mm-hmm.
Is there any aspect of like security and trust and that kind of thing?
Oh, absolutely. I mean, effectively running a Docker container isn't dissimilar from curling something into bash. Like, it's not, that's what it is, right? You're doing curl some URL pipe sudo bash. That's what it ultimately is. And you kind of have to be comfortable with that and do your own due diligence. One of the biggest failings of Docker, I would say, is that it kind of is so tightly coupled to Docker Hub. So I have to trust what is in Docker Hub, and running my own repository isn't trivial. And even once I have it set up, pulling images from my own repository isn't trivial.
But you always check the MD5 of every image you download before you run it, right?
Oh, let me tell you, all the time. But you know, that's even scarier, because like there are quite a few exploits that if you, to use my curl example, where if you just curl it, you will get back a legitimate file, but once it detects that it's just being piped into something else, becomes another file. So like, there's ways around that, and like, yeah, you should vet all of your Docker containers. It's like NPM packages. Like, there was a blog post about a month ago about how NPM is a terrible thing and could be really, really terrifying, and someone with just a little bit of malicious intent could easily get into like is odd, which is pulled by literally every other package that exists. So like, yeah, you got to do your own due diligence there, especially because running inside of a Docker container, you are running as root. So the more things you have control over will be more secure. So for example, whenever I was working at Fitbit and whenever I talked to Facebook, the biggest problems they had with Docker as a containerization technology was that. Like that's why it's not being used at some bigger places. So for that specific example of, good call. So the question was ultimately, because of what we just talked about with Docker Hub, can you point it to something like GitHub where a Docker file exists? And the answer is no, because a Docker file is like the source code. It hasn't been compiled yet, right? But what you can do is like AWS has an Elastic Container Registry. So like that's something we use internally and have had great success with. So a Docker file isn't enough. You had to have built it and then upload it somewhere, which kind of gets to a little bit of a catch-22 with Docker, because it's really easy to have your deployment process be, well, I did a git pull on this machine that now has a Docker file, and now I'm doing a Docker build and I'm running it. That's not an uncommon process, but you shouldn't ship build processes. You should ship artifacts, right? So the solution to what you're alluding to is that you need to run your own registry. And really, to me, Docker doesn't become an enterprise-ready tool unless you're running your own registry. Otherwise, you're completely at the mercy of whatever joker's gotten out there ahead of you. But that's also the same question as like, yeah, but I trust apt-get. So you kind of have to decide your own risk level. Like, if I want to be secure with apt-get, I run apt-cache-ng. You know, it's that kind of thing. Does that answer the question? All right, cool. Anything else? All right, cool beans. Well, thank y'all for coming. Grab a beer, grab some snacks. There's cookies over there. They're good cookies. And yeah, thank you, everybody.